Hello, my name is Martin Luca, and today I want to talk to you about joint work between my colleague from American University of Sharjah, Khaled Al-Faki, and myself, and our joint work on the determination of the exact length of the distinguishing sequences of a specific subclass of reversible finite state machines. So now finite state machines are essentially tools or a state transition systems that have a finite number of inputs, outputs, states, and also a finite number of transitions that are labeled by a pairs of input and outputs. Now, these FSMs, defined as these tools, are used in many branches of engineering, such as software engineering, digital computing, game design, simulation and analysis of sequential and digital logic, and so on. In particular, these tools are very famous for the ability to provide a very good methodology for design and verification. Now, similarly to any other tools, when new computing technology arrives, such as quantum computing or reversible computing, this tool needs to be adapted and revised. And therefore, in this work, we are looking at a specific properties of these finite state machines adapted to the reversible computing. Now, a finite state machine is essentially a sextuple defined by a set of states, defined by an initial state, defined by a set of inputs, set of outputs, and two transition function. Delta is a next state function of the form for s times x given an x, which means for a state and an input, a new state is generated. And we have the output function that for a given state and an input, a next output is generated. An example of definition of a finite state machine can be seen in table A, where you can see on the left side under S, we have all the states, present states. We have input 0, 1, 2, and for every combination of state and input, we have a new state and new output generated. Now, similarly to FSM, the reversible FSM is also defined in the same way, with the only difference that we define a function f that takes as input a state and an input and generate as output a next state and new and an output. And because if it is reversible, it means that if we apply the inverse function f minus 1 on the output and the obtained state, we will obtain the input and the previous state. Now this is shown down in definition. An example of such a machine is shown in figure B or table B, where actually we can see that every combination of output and state is unique, and therefore it is possible from every output and combination of output and state determine what was the previous input and state. Okay. Now, the specific properties that we are looking at are called the distinguishing sequences, and the distinguishing sequence is essentially a testing facility that allows to determine a particular hidden state or any hidden state of a finite state machine. For instance, let's say that we have a machine in an unknown state, and it is represented by the uncertainty showing all four states. So if the machine has four possible states, and if we don't know which one is it, we say that the machine is in A, B, C, D, because any of the state is possible. Then by applying a specific sequence of inputs, we will observe the set of outputs, and this set of outputs will give us the information, or not, will not give us the information about what was the hidden state. Now, if such a sequence exists, the machine has a distinguishing sequence. If such a sequence doesn't exist, such a machine doesn't have distinguishing sequence. In this particular work, we're going to be looking at the length of this distinguishing sequence for reversible finite state machines. Now, before continuing, we want to introduce one more finite state machine, which is called the output balance reversible finite state machine, and it is defined that for every input of this reversible finite state machine, the balanced distribution of output is generated. So as you can see, for instance, table A, for input 0, we have 2 1s and 2 0s generated. For input 1, 2 1s and 2 0s are generated. Therefore, this is an output balanced machine. On the contrary, in the machine shown in table B, we see that for input 0, we have 3 1s and 1 0 generated, and for input 1, we have 1 1 and 3 0s generated. Therefore, it is not a output balanced machine, even though it is still reversible. Now we're going to be looking at these output balance machines, and in particular in some specific types. The first type is such a reversible final state, output balance reversible final state machine that has the same number of states as number of inputs as number of outputs. It is a nice and square, and the very interesting thing about this machine that it has a distinguishing sequence of length 1, which means if you are in an unknown state, you apply an input, and for that particular input you will have a unique output and state that will directly allow you to identify the hidden state of your final state machine. A little bit more complex case happens when the number of state is modulo number of inputs is equal 0, which means the number of state is a direct multiple of number of states. As for example, here we have a machine in table A where the number of states is 4, number of inputs 2, so 4 modulo 2 is equal 0. Yes, and similarly to the machine in table B. Now the length of this distinguishing sequence here, essentially it is a product of the number of inputs and of a ratio of number of state divided by number of inputs. Now, for the details about the proof, it's shown in the paper, and the general idea is that once we have an output balance machine, in order to break any of these groups, grouped by same state, we need at least y inputs, or y times application of inputs, so that actually we can see that from arbitrary group we arrive to somewhere where this particular group is broken. Finally, the third type of machine that we are looking is the such a machine where the number of state is not a direct multiple, let's say, of the number of inputs, which means S mod X is larger than 1, and in particular for output balance reversible final state machine, such a machine doesn't actually exist. Now in the paper we continue this analysis for output unbalanced final state machine, and we find in general that most of these machines, well, they have a sequence much shorter than the exponential bound given by Kohavi for the general types of machine. And so when we found that the bounds are relatively reasonable compared to arbitrary final state machine, of course they have a restricted power. And because of this, we plan to extend our work to conservative RFSMs to see how they fares with distinguishing sequences. We believe that they will be even more restrained because conservative RFSMs are even more restricted. And in addition, we also plan to extend this analysis to synchronizing sequences as well as truly quantum final state machines. If you are interested in more details, please consult our work, our talk in YouTube or the paper by this conference. Thank you very much. Thank you for listening. And if you have any questions, please do not hesitate to ask.